Welcome back. We continue with our mode concept topic. Here we want to look at part 2. Remember, part 1 we did up to Gay-Lussac's law and we did a lot of examples. So now let us move ahead to the next subtopic in this particular topic. So the next subtopic is about ionic equations. What are ionic equations? Remember, this topic we are covering both the mole concept and ionic equations. An ionic equation is a chemical equation showing movement of ions, that is cations and anions, from reactants to products. Remember that solids, gases and liquids do not ionize. The only items that ionize are compounds in aqueous solutions or in molten state. So you find that in a reaction where there is metals and all those other gases, liquids, the solid state that don't ionize, you'll find that the ionic equation will only concentrate on the ions, the aqueous solutions or molten state that ionize and the product that they create. Let us look at various examples of ionic equations. We start with the precipitation of insoluble salts. All insoluble salts are prepared through double decomposition or precipitation, which involves mixing two soluble salts to form one soluble and one insoluble salt. An example is reaction between silver nitrate and sodium chloride to produce silver chloride and sodium nitrate. This is the equation for the reaction, as you can see here. So where we have AgNO3, which is aqueous, plus NaCl, which is aqueous, to form AgCl, which is a solid, and NaNO3, which is aqueous. These are silver nitrate and sodium chloride to form silver chloride and sodium nitrate. So in terms of the ionic equations, what you do, you break the compounds into their ions. That's why in silver nitrate you find there is here, I'm putting silver, this silver ion, then nitrate ion, sodium ion, chloride ion, to form silver chloride, which is as we said is a solid, so it can't ionize. Then sodium nitrate, which ionizes to sodium ions and nitrate ions. So once you do that, then you cancel out those that balance, those ones that are on this side, the reactant side and product side. So here nitrate will go away with the nitrate on this side, then sodium will go away with the sodium on this side, and therefore you are left with the silver ion and chlorine ion to form what we call silver chloride. That is the final ionic equation. Another example of an ionic equation can be through neutralization, whereby there is a reaction between acid with a soluble base or alkali or an insoluble base. Reaction of an acid with a soluble base or alkali or an insoluble base. An example is nitric 4 acid and potassium hydroxide. As you can see, this nitric 4 acid reacting with potassium hydroxide to form potassium nitrate and water. If you break down into ions, you'll have hydrogen ions, nitrate ions, potassium ions and hydroxide ions to form water, and nitrate ions and potassium ions, sorry. So you can cancel out what is this side and the other side. Nitrate is here and nitrate is also here in the product side. Potassium is here in the reactants and also in the product side, so both will cancel out. So we'll be remaining with hydrogen ions and hydroxide ions to form water, which is the final ionic equations. Another example is sulfuric acid and ammonia solution, which as you can see here, this is the equation. Once you break down into ions, you can see the hydrogen ions, sulfate ions, ammonium ions, hydroxide ions to form ammonium, sulfate ions and water. So once you cancel out the ions that are on both the reactant and the product side, you remain with hydrogen ions and hydroxide ions to form water. So that is the final ionic equation. So I want to believe that we are good there. Let us go to the other subtopic, which is molar solutions. Molar solutions are solutions whose concentration is known. The SI unit for concentration is molarity. So once you are asked about the concentration of a solution, you are being asked about the molarity of that solution. And molarity is normally the number of moles of a solute present in 1 cubic decimeter, or in 1 liter, 1000 centimeter cubic of that particular solution. For an example, 2 moles sodium hydroxide means that you have 2 moles of sodium hydroxide that have dissolved in enough water to make 1 cubic decimeter or liter, 1000 centimeter cubic uniform solution mixture of sodium hydroxide and water. So now I want to believe that it's clear there what molarity is. So let us look at examples. Calculate the molarity of a solution containing 4 grams sodium hydroxide dissolved in 500 centimeter cubic of a solution. As we have said, the molar mass of the molar mass of sodium hydroxide is 23 plus 1 plus 16, which gives you 40 grams. Moles in 4 grams is equal moles in 4 grams. This is how you do it. You divide 4 grams with 40, which is the molar mass. You get the moles to be 0.1 moles. So then you say 0.1 moles is in 500 centimeter cubic. Remember, we have been asked about 4 grams dissolved in 500 centimeter cubic. So 500 centimeter cubic gives you 0.1 moles. What about 1000 centimeter cubic? You do your cross multiplication and you find that the molarity is 0.2 mole. The other question is 5.3 grams anhydrous sodium carbonate dissolved in 50 centimeter cubic of the solution. It's the same thing. So you take molar mass, which is 106 grams. You molar mass of sodium carbonate. Then moles in 5.3. You divide the 5.3 with 106, and then you find that the moles in 50 centimeter cubic will be 0.05. So you say 50 centimeter cubic is 0.05. What about 1000 centimeter cubic? You do your cross multiplication there, and you find that the answer is 0.5 moles. Another example is the density of sulfuric acid is 1.84 grams per centimeter cubic. Calculate the molarity of the acid. That is quite simple. You take the molar mass of sulfuric acid, which if you calculate is 98 grams, then moles in 1.84 grams. We are told that what you do, you divide 1.84 by 98, you get it to be 0.019 moles. So 0.019 moles is in 1 centimeter cubic. Remember, we are told that the density is 1.84 grams per centimeter cubic, 1 centimeter cubic. So 0.019 moles is in 1 centimeter cubic. What about 1000 centimeter cubic? You do your cross multiplication and you find that the answer is 19 moles. So enough there on molarity. Let us now go into titration. This is the core of this mole concept topic, and normally this is common even in your practicals, when you are doing practicals in chemistry. So let us go down there and do several examples. Okay, volumetric analysis or titration is the process of determining a known concentration of one reactant from a known concentration and volume of another. Reactions take place in simple moles ratio of reactants and products. The relationship is, as you know that normally the stoichiometric equations are key to chemistry, and once you write them and they balance, you are able to know the ratio of reactants into products. Then from there it becomes very easy even to do these particular titration equations. So the formula, the relationship for calculating these concentrations and volumes is that M1V1 over M1 is equal to M2 V2 over M2, where M1 is the molarity of reactant 1, M2 is molarity of reactant 2, V1 is volume of reactant 1, V2 is volume of reactant 2, M1 is number of moles of reactant 1 from the equation, and 2 is the number of moles of reactant 2 from the equation. Let us do examples. Calculate the molarity of MCO3 if 5 centimeter cubic of it reacts with 25 centimeter cubic of 0.5 mole hydrochloric acid, and you are given there the molar masses of the reactants. So the first thing you do is you write the equation. As you can see, MCO3 plus 2 plus HCl gives you MCl2 plus CO2 plus H2. You balance the equation, you find that 1 MCO3 reacts with 2 HCl to give you MCl, CO2 and H2. So you can you can calculate using our formula of M1 V1 over N1 is equal to M2 V2 over M2. Therefore, M1 we don't know because that's what we are looking for, molarity of MCO3. So M1 times 5 divided by 1 is equal to 0.5 times 25 over 2. Remember, we are told that 0.5 is the molarity of hydrochloric acid, and then we are using 25 centimeter cubic, and of course we have seen from our equation that 1 MC2 is reacting with the 2 HCl. So N1 is 1 and 2 is 2. So you put that in that equation, you do your calculations, and once you do calculation, you make M1 the subject of the formula. You find that the molarity of M1 is the molarity of MCO3 will be 1.25 moles. So let us do practical titrations, which are very common in your practicals. And the general procedure is that you fill a burette with known and unknown concentration of a solution, one of the reactants. Then you add the solution to unknown known concentration of another solution in a conical flask until there is a complete reaction. When both solutions are colorless, an indicator is added to the conical flask. When the reaction is complete, a little excess of burette contents changes the color of the indicator. This is called endpoint. This one, I know you've been taught, and you will be taught also. And again, you will do a lot of them in your practicals. Titration is very common in chemistry practicals. A titer is a final burette reading minus initial burette reading. Results are recorded in a titration table. Let us do our practices. At least you know the procedure. I know you've done in your laboratories, and you know how the titration is carried out. What I want us to look at is how to undertake the calculations. Let us look at the practice 1, where you are provided with 0.1 mole sodium hydroxide solution A and hydrochloric acid solution B. You are required to determine the concentration of solution B in moles per liter. And then we are told the procedure is that you pipette 25 centimeter cubic of solution A, which is sodium hydroxide, into a conical flask. Then you fill in the burette with solution A. Titrate solution A with B using phenolphthalein indicator and complete the titration table. From this example, we are assuming that the titration table was as recorded as being indicated here, where the initial initial readings were 20, final readings initial readings were 0, and final readings were 20. So the amount of B used was 20 in every one of the 3 titrations. So you are asked first to calculate the average of solution B used. Here we have 3 titrations, so you take 20 plus 20 plus 20 divided by 3 because there are 3, and you get your average to be 20 centimeter cubic. Question number 2. How many moles of solution A were present in 25 centimeter cubed solution? Remember, we have been told that 0.1 m is the molarity of solution A. Therefore, the molarity means the amount of moles in 1000 centimeter cubic. So 0.1 m is in 1000 centimeter cubic. What about 25 centimeter cubic? And once you do your cross multiplication, you find that the correct number of moles is 0.0025 moles. Then how many moles of solution B were present in the average volume? Here what you need to do is first to write the equation. The equation is, as you can see, sodium hydroxide plus hydrochloric acid gives you sodium chloride and H2O. You balance, you find that the ratio is 1:1. Therefore, if you found that the moles of sodium hydroxide were 0.0025, that means the same is the number of moles for B, which is hydrochloric acid. So the number of moles here is also 0.0025. This is because the ratio of reaction is 1:1. Then another question is moles in solution B in moles per liter. 0.0025 we have found is in 20 centimeter. Remember, we found that our average volume was 20 centimeter. So 0.0025 moles is in 20 centimeter cubic. What about 1000 centimeter cubic? You do your cross multiplication and you find that the molarity of solution B is 0.01 moles. So that is it. Let us look at the second practice question, which is redox titration. So in this titration, you are provided with acidified potassium manganate solution A. You are also provided with 0.1 mole iron 2 salt solution B, and you are provided with 8.5 grams of ammonium iron 2 sulfate crystal, which you've been given the formula there. You've been given the formula there with some, you can see there is some X here. So even you find there is some X in the formula, that tells you that at some point you'll be told to calculate the value of X. So let us get going. So you are required to standardize acidified potassium manganate 7. You are also supposed to determine the value of X in formula, as I've told you. So the procedure is fill the bullet with the solution A, which is acidified potassium manganate. Pipette 25 centimeter cubed of solution B, which is iron salt solution. Titrate solution A with B until a pink color just appears. Record in the findings. From this example, the average for B was also found to be 20, because every titration has 20 and we have 3 titrations. Calculate the average volume of solution A, solution A that was used, solution A or solution B. Calculate the average of solution B. So what you do, you add the 3, you divide by 3, you get it to be 20 centimeter cubic. How many moles of solution B were present in 25 centimeter cubic? So we are told that solution B, the molarity is 0.1 mole. So that tells you that in 1000 centimeter cubic you have 0.1 moles. What about 25 centimeter cubic? You do your cross multiplication, you get it is 0.0025 moles. The other question is solution A. How many moles of solution A were present in the average volume? Assume 1 mole of A reacts with 5 moles of B. So you've been given the ratios there, because you cannot be able to do the equation now, but you have been given the ratios that 1A reacts with 5 B's, and we have already seen that B is 0.0025. So what do? You just mole ratio is 1:5, so 1 mole of A is 5 moles of B. So if 0.0, what about if where here when we found that the number of moles of B is 0.0025, then what is the number of moles of A? You do your cross multiplication and you get that what you need to do is to divide 0.0025 by 5 and get that the solution A, number of moles present in solution A in the average titer is 0.0005 moles. The other question is how many moles of solution A in moles per liter, that is molarity. Already we know that 0.0025 moles are in 20 centimeter cubic. What about 1000 centimeter cubic? You do your cross multiplication and you get that it is 0.125 mole. So the other part of this practice in the same question is that you place all solid C into 250 centimeter cubic. Remember our solid C here was 8.5 grams of ammonium iron 2 sulfate, which we have a formula there with an X somewhere. So what you are supposed to do, you are required to do, is to place all solid C into 250 centimeter cubic volumetric flask. You add about 200 centimeter cubic of distilled water, shake to dissolve. Make up to 250 centimeter cubic of the solution by adding more distilled water. Label the solution C. Pipette 25 centimeter cubic of C into a canonical flask. Titrate solution C with solution A until a permanent pink color just appears. Complete the table. For this example, the table was completed and the average was still 20 centimeter cubic. So you calculate the average. 20 plus 20 plus 20 divide by 3, which is 20 centimeter cubic. Then how many moles of solution A in the average titer? So we are saying the molarity of A, you had found it to be 0.125 in the previous example here, in this previous calculation here. So what you need to do is to 0.125 is for 1000 centimeter cubic. What about the average, which is 20 centimeter cubic? You do your cross multiplication, and you get that the number of moles is 0.0025 moles. So part 2, solution C in 25 centimeter cubic solution given the equation for the reaction S. Here we are looking for number of moles. We are looking for how many moles of solution C in 25 centimeter cubic solution given the equation for the reaction to be that, as you can see there. So from there, mole ratio of manganese oxide, manganese and iron is 1:5. So we are saying 1:5, and we have seen for A it was 0.025 moles. So what about C, which is iron? So once you find that, what you need to do is to multiply, and you get that the number of moles of C in 25 centimeter cubic will be 0.0125. Is 0.0125 moles. So what about in 250 centimeter for solution C? So we found that 0.0125 moles is in 25 centimeters. What about 250 centimeters? Once you do your cross multiplication, you get that the number of moles of C in 250 centimeter cubic will be 0.125 moles. So the next question is calculate the molar mass of C, and hence the value of X in the formula. So what do we need to do? We first, what we do, molar mass, the way you calculate it is that you take the mass that we have given to be in 250 centimeter cubic, and which is the whole content of C, which was 88.5 grams. You divide by moles in 250 centimeter cubic, which you have found to be 0.125 moles. So what you do, you divide the 8.5 that we dissolved in the 250 centimeter cubic, 8.5 grams, you divide by the moles in that particular volume, which is 0.125, and we get that the molar mass is 680 grams. From now here, you can be able to determine the value of X, because now you know the molar mass of N, of H, you know the molar mass of S, you know the molar mass of oxygen, iron, S, O, H, O. So now you replace each one of them with their molar mass, and where you need to multiply, where there are brackets, you multiply. So you get that NH4 times 2 is 36, plus 32 for S, plus 64 for 4 oxygens, plus 56 for iron, plus 32 for sulfur, plus 64 for 4 oxygens plus this water which is 2 for oxygen plus 16 which is 18, which is the one being multiplied by x. So plus 18x is equal to 680. From there you can be able to complete the calculation and find that your x is equal to 22. Let us look at the final practice, which is back titration, where we have 3 reactants. In back titration, we always have 3 reactants. You are provided with an impure calcium carbonate labeled M. That is calcium carbonate that is mixed with other dyes. It is not pure. Then you are provided with hydrochloric acid labeled N, and you are also provided with solution L containing 20 grams per liter of sodium hydroxide. So you are required to determine the concentration or molarity of N, which is hydrochloric acid, and also the percentage of calcium carbonate in the impure mixture M. So let us get started. The procedure is that you pipette 25, procedure 1, you need to pipette 25 cm cubic of solution L into a conical flask. Add 2 to 3 drops of phenolphthalein indicator. Titrate with dilute hydrochloric acid solution N and record your results in table 1. Our table 1 is like that, and you find that the average volume there came to 6.5 because it was 6.5 for each titration. So how many moles of sodium hydroxide are contained in 25 cm cubic of solution N? Solution N. We are told that 20 grams. Remember, we have been told that for solution N, hydrochloric acid, for solution L, we've told that it contains 20 grams per liter of sodium hydroxide. So if you are calculating for 25 centimeter cubic, 1000 centimeter is 20 grams. Then you are supposed to calculate for 25 centimeter cubic. Once you do your cross multiplication there, you get 0.5 grams. Now with that, you can convert that to mole by dividing by molar mass of sodium hydroxide, which is 40. So you get that the moles are 0.0125. Then calculate the number of moles of hydrochloric acid that react with sodium hydroxide. You can do you start by writing the equation. You find that the ratio is 1:1, and sodium hydroxide is to hydrochloric acid, and therefore if moles of HCl were 0.0125, then it means also, moles of sodium hydroxide were 0.0125, it means that the same applies to hydrochloric acid. Then we are supposed to calculate the molarity of hydrochloric acid in solution N. So 0.0125 we have found is in 6.5 centimeter cubic, which was our average volume. Then you need to calculate for 1000 centimeter cubic. You do cross multiplication and you find that the molarity is 1.923 moles. Then we go to procedure 2. Procedure 2, you place the 4 grams of M provided into a conical flask. Remember M was an impure calcium carbonate. So you take 4 grams of that and place in a conical flask, and add 25 centimeter cubic of dilute hydrochloric acid. So here you are adding 25 centimeter cubed of hydrochloric acid to it using a clean pipette. Swirl the contents of the flask vigorously until effectiveness stops, until the reaction is completed. Then using 100 milliliter measuring cylinder, add 175 centimeter cube distilled water to make up the solution up to 200 centimeter cubic. Remember, we had first added HCl, hydrochloric acid, 25 centimeter cubic. Now when we add 175 centimeter cubic of water, we are diluting it further and creating a total of 200 centimeter cubic. Label this solution K. Using a clean pipette, transfer 25 centimeter cubic of the solution into a clean canonical flask and titrate with a solution L from the burette using 2 to 3 drops of methyl orange indicator. Record your observations in table 2. So in this example, after recording, we get an average L of 24.5 centimeter cubic. Calculate the average volume of solution L used. You find that the average comes to 24.5 centimeter cubic. How many moles of sodium hydroxide are present in the average volume of solution L? So remember we found that 0.0125 moles was present in 25 centimeter cubic. What about 24.5 centimeter cubic? If we do a cross multiplication, we get that it is 0.01225 moles. How many moles of hydrochloric acid are present in the original 200 centimeter cubic of solution K? Original is now before we extracted the 25 centimeter cubic for this titration. So what you need to do is to get that the molar ratio of sodium hydroxide to hydrochloric acid is normally 1:1. Therefore, moles of hydrochloric acid used is 0.01225 moles. So 0.01225 moles is in 25. Remember here we picked only 25 for this titration. Therefore, what about 200 centimeter cubic? If you do a cross multiplication, you find that it was 0.098 moles. Then how many moles of hydrochloric acid were contained in the original 25 centimeter cubic solution? So here we are saying 1.923 is, remember 1.923 we had solved to be the molarity of hydrochloric acid. So 1.923 moles is in 1000 centimeter cubic. What about 25 centimeter cubic? So once you do your cross multiplication, you will find that the number of moles that were present in the 25 centimeter cubic was 0.048 moles. Then how many moles of hydrochloric acid were used to react with the calcium carbonate? Remember, before we put it into, we used, so we have found that here, remember we have found that here, that the number of moles in the original 25 centimeter cubic, where we had put all the 4 grams of M into the hydrochloric acid, was 0.048 grams of moles. And also here we are aware that after the reaction 0.01225 of hydrochloric acid has been used in this titration. Therefore, we can be able to determine how many moles of hydrochloric acid were used to react with calcium carbonate present. So what we need to do is to we get the original moles, then we minus the moles in the average titer, or the moles that have been used in the second titration. So you get 0.048 minus 0.01225, and you get that the resultant amount of moles of hydrochloric acid that reacted with calcium carbonate to be 0.03575. So write the equation of the reaction between calcium carbonate and hydrochloric acid. The reaction, you can be able to write that equation and balance it, and you find that 1 calcium carbonate reacts with 2 hydrochloric acids. To calculate the number of moles of calcium carbonate that reacted with hydrochloric acid, as I've said, the ratio is 1:2, and we are aware that the hydrochloric acid is 0.03575. So how do we get the number of moles of calcium carbonate? We divide by 2 and we get it to be 0.017875 moles. Calculate the mass of calcium carbonate in 4 grams of mixture M. So we are saying the molar mass of calcium carbonate, if you do your calculations there, 40 plus 12 plus 48 is 100 grams. 1 mole is therefore 100 grams. What about 0.017875 moles? That will give you 1.7875 grams. Then our final question is determine the percentage of calcium carbonate present in the mixture. So you take what you have gotten there, 1.7875 grams, you divide by 4. Remember we'd taken 4 grams, then multiply by 100 and you get your 44.6875% as the answer. So thank you very much. That was the topic, more concept. I know we have done it very fast, but get some time. Next we'll be doing questions on this particular topic, because this one you can be able to understand it well after doing a lot of practices. So in the next few sessions we'll be tackling questions on more concept. Thank you and see you next time.